We've had a nice chat, I hope, and we know each other somewhat. And basically, we're covering a series of papers that we're going to take inspiration from and using the science from for our own project. These are all like preliminary research that we're grabbing for our ANA project, which is essentially this skin flush device, sits on the forehead, and reads biosignals. And it's a pretty big leap for us. So we had to make sure we use accurate papers, reliable, and they're reputable, and we can recreate them in the lab. So the papers had to be well documented, clear steps. And in the previous talk, I talked about the overview of some of these devices, these skin-like electronic devices, and it was just a quick cover of exactly what we can do with this. And for example, these electrodes that they've printed onto the head. Nancy Liu, I can see that she is pioneering this in Texas, Austin, and it's amazing what we can do with these very skin conformable wearable technology, which I think what we're headed in. And I want to go lead into or stay on this slide because today Brish is going to talk about specifically the materials. This is probably one of our unknowns for our project because we have not done any sort of material engineering before in our lives. Brish and I are definitely much out of our depth. So the last few months we've been speedrunning as much as we can material engineering without the degree. And just I briefly talked about it last time I was here in the journal club, and how basically the common factor between all of these materials was that PEDOT PSS was the wonder polymer, bioelectric polymer. It was conductive, it was breathable, it was flexible, and it was mixed with different things. So in this non-Chinese e-tattoo, specifically here, there was PDMS and glycerol with certain ratios and tuning. So tuning being that you mix certain things together that allow it to have these certain properties which are desirable for this purpose. And there's like so many other variations and so many other combinations that we can explore and that are used in different research. And this might not be what we want. We're looking for a sensor sheet, not a tattoo. So that completely changes, surprisingly, just changed the tuning that we want inside of it. So as you can see in the diagram, there's PSS, PEDOT. It's a cover for a very long chemical name, nothing crazy, but essentially it has some special properties that allow it to easily curate onto the skin. And today we're going to talk about some different variation from a Japanese university, and it was, if I were to just change this, hold on a second. We are now going to talk about one of the other papers today. And the first paper that we took inspiration from, that we realized is pretty complicated actually, is a different one, which is basically a transparent sensor sheet. Is it more than a tattoo, which isn't printed on per se by an inkjet printer? It's laid, it's plastered onto your forehead, and it has some very different tuning, and it's slightly different. It varies slightly differently from the paper I covered last time, in a way which is different. Again, different components to it. It serves different purposes. It's meant for longer term wear, longer term uses, and more consumer healthcare rather than what Nancy Liu's paper was more clinical. It seemed like it only lasted for less than a day and 6 hours or so, which isn't ideal, I guess. I thought we could do better. And this, just out of the top of my head, not to steal any of Brish's flair, but it's like, PEDOT PSS is in here. And we're definitely going to be using it for our project. And it has some other tunings to it. It has, I think, glycerol, something glycerol in it, and GOPS, some other chemical components, which Brish will explore today. So without further ado, I'd like to bring on Brish to the stage. She'll be talking about the materials side from this paper. And yeah, it's all yours.
Thank you very much. Hello guys, thank you so much for coming today. I didn't expect such a good turnout, so I really appreciate you coming. I just want to give you guys some context on who I am and why I'm talking about this paper today. So my name is Brishti. I'm a final year biochemistry student, undergrad. I just finished my degree. So I'm very unfamiliar with material science and biomedical engineering. I'm really putting myself out there, and I'm trying my best to learn a lot about materials and about neuroscience, especially with the help of Damir and his passion for neuroscience. I'm very grateful to be up here talking about this today. So if I get anything wrong that is a bit obvious to you guys, feel free to give me some constructive criticism. It would really help me out, and it would also help the team out. But yeah, so I decided to use this paper because this paper gave us a lot of inspiration for what we want to do. Yeah, please fix that.
Yeah, just put it on.
So
Yeah, perfect.
does that work?
Yeah.
Cool. So yeah, firstly, I'd like to go over what our project is in case you're not aware. So Anna is this idea that we're still kind of iterating through. We're thinking that it will be a sticker that you stick to your forehead, and it allows reliable and very convenient and affordable measurement of your brain waves. So we're hoping that this can be used to measure your focus, so we can quantify your focus, and we can also quantify your emotional state. So this would be great for people going through therapy who are trying to help themselves regulate their emotions better. So you can put on your sticker and then open the app and then see how your mood is going. And then maybe you can do some exercises like a meditation and see how these meditations improve your emotional state, or maybe even your focus. So I think this would be a great supplement to therapy. We're still in process of chatting to potential customers to see what they think of this idea, but this is what we're thinking of right now. So what are some challenges that we're facing today with regards to measuring our brain data, and why are we building Anna? So if you don't know, an EEG is a medical instrument that doctors use to measure your brain signals. So the first point is that it's highly technical to use. We need very trained people to set up an EEG. So it's quite complicated, and it's very bulky. It's not generally for the normal person to use on a daily basis. And a second thing that is a huge consideration is high impedance. So what impedance means is that there's a lot of resistance between the brain electrical signals and the actual sensor of the EEG. So the electrical brain signals that come from your brain are actually very minute. They're the smallest signals that come out of your body. So there's a lot of noise that interferes with the signal. So we want to improve the impedance. So we want to reduce the resistance that the sensor is picking up on. Next is comfort. EEGs are generally very bulky. You can't put it on in your bedroom. You can't fall asleep with it on. And people also report a lot of skin irritation when they wear EEGs. So we want to produce something that is wearable to the users as well. Motion artifacts is another important point to make. Usually when doctors measure brain signals using EEGs, it's in a very quiet room. The patient isn't supposed to move. They're supposed to sit very still. It's very noisy. So every time you take a step or you blink or you grind your jaw, there are artifacts that mess up the data. So we want to see if we can, I think our product won't be able to get rid of the artifacts, but maybe later along the line with machine learning, we can get rid of this noisy data. Next is skin preparation. What doctors generally use is that they generally use wet electrodes. So they prep the skin. You have to kind of clean the skin first, and then you need a gel, and then you put the electrode onto the skin. And this gel is what improves the impedance, and it also improves noisy data. So we want to make our product easier to use. So we don't want to have to clean our skin, have a gel, and then the gel dries up, and then the sensor isn't usable anymore. So we want to make a material that overcomes the skin preparation step. Finally, limited duration. I just touched over this. When you add the gel to your forehead, it dries up eventually, so you can't actually use the electrodes for very long. So our material aims to be able to be used for maybe even 24 hours, or maybe even for several days of the week. Who knows? Very early stages. So yeah, so we think that a soft electrode would be a very good solution to these problems. Soft electrodes are affordable, they're comfortable, they're small and compact, so I think they're very usable to the common customer. So yeah, they're non-invasive, you just stick them to your skin, there's no inflammation if you use the correct materials, and they're stretchable. The thing about skin, when you put something onto your skin, the material has to be stretchable because the skin is stretchable. You raise your eyebrows, you might furrow your brows, making the skin on your forehead stretching throughout the day. So we want this material to be stretchable to improve comfort and to also improve the electronics inside the material. We also want it to stick to the forehead. This is quite important, and I will touch on adhesion in a moment. Something else about this material is that we want to be able to manage the properties. What this means is that we want the material to be stretchable, but at the same time, we want it to be conductive so that the electrical signals coming from your brain can be read by the electrodes themselves. So this paper offers a method to create this material. We've taken a lot of inspiration from this paper. And what this paper does is that it fuses organic and inorganic materials. So in this presentation, I will cover the organic material and I will also cover the inorganic material. I will also explain how this paper describes the optimization of the desired properties. So we want to optimize stretchability, we want to optimize adhesion. At the same time, we also want to optimize conductivity. I will also briefly go over the fabrication techniques that they use, and briefly why they use these specific fabrication techniques. And I will also go over how the material performed. So do customers actually want to use this material? Is it comfortable enough? And is it feasible to sell in the market? So I'll briefly go over the organic material. So remember, this material is made out of an organic material and an inorganic material. The organic material is made of two types of polymers. So firstly, there's a stretchy elastomer. So the elastomer is either made out of acrylate or PPO-PSI. So PPO-PSI stands for a very long chemical. I can't remember the name. But yeah, so we want a stretchy elastomer with a conductive polymer called PEDOT PSS. So we're actually mixing both of these types of polymers together. Interestingly, what this does is that they don't actually mix very well. When you mix liquid polymers, they phase separate. So what that means is that if you look at the image to the left, you can see that PEDOT PSS actually agglomerates. And the elastomer forms the kind of liquid surrounding the PEDOT PSS agglomerates. So this is actually beneficial. I'll explain why these agglomerates are beneficial in a moment. But we can see that, that when you have these PEDOT PSS agglomerates with an overall elastomer area, we actually get the benefits of both the stretchiness and the conductivity. So why is it so beneficial that we have PEDOT PSS agglomerates? Remember, PEDOT PSS is the conductive polymer, and this is what actually allows the electricity to be read by the electrodes. So let's see if I can explain this. So we can imagine this as a sheet. Yeah, it's kind of a sheet, right? Yeah. So yeah, imagine a sheet of the pink elastomer, and then there are kind of dots of the blue PEDOT PSS. It's not blue and pink in real life. This is just an illustration. And when you stick this sheet to your skin, we want the electrical signal to come out of the skin and then go outwards towards the electrode. We don't want the electrical signal to go into the sheet and then go sideways, if that makes sense. We want it to go out and be read by the potential electrode. So the fact that there are agglomerates means that there are these holes where the electrical signal kind of just comes out of. Does that make sense to everyone? I don't know if I explained that very well. So that's the benefit of the agglomerates. So so yeah, rather than the electrical signal moving sideways, within the plane of the sheet, it goes vertically, so it goes straight through the sheet and then out to the electrode. That'll pick up the signal. So how can we further optimize the elastomer PEDOT PSS material? Once again, we want to improve the elasticity, we want to improve the conductivity, and we want to improve the adhesion. So the larger the agglomerates, the worse the impedance. So what this means is that when the PEDOT PSS splotches, I guess, are larger, the signal is worse. The signal is worse because of this lateral movement of the signal. Also, when we increase the PEDOT PSS content from 2% to 9%, contact impedance improved. So the lower the contact impedance, the better. So at a higher concentration of PEDOT PSS, the impedance was reduced to only 19 kiloohms. Is that ohms? However, even though impedance was reduced to 19 kiloohms, this did not improve the EEG signals. Why? As I explained before, this is actually a much better illustration of what I was trying to explain earlier. When you have the bigger splotches, the signal can move, I guess, laterally. Is there a, yeah, I can't really use the laser, can I?
We use the cursor.
Yeah, that's okay. And then, yeah, so, but then when we use a lower PSS concentration, we have smaller splotches, which improves the signal. It allows more of the vertical transduction of the signal. So another way to improve the signal of the EEG is by adding silver and silver chloride particles. That is silver, right? Yeah, so silver chloride. Yeah, so what silver chloride microparticles do is it actually helps the agglomeration of PEDOT PSS. So we want these agglomerates within the elastomer. We can add silver chloride to improve to reduce the size of these agglomerates, but also increase the number of these agglomerates. So this helps the stretchability of the material because there's more space covered by the elastomer, but it also increases the conductivity of the material because it increases the number of these agglomerates, but it also reduces the size of these agglomerates. So the signal is better read by the electrode. Great, so now that we know the properties of the organic material, I just want to cover the fabrication methods that were used to create this material. And this may inspire what we do within the lab. So there's this blade coating technique, which was used for the elastomer made out of acrylate. So remember, there were two types of elastomers. There was the acrylate elastomer, and then there was a PPO PSI elastomer. This paper experimented with both of these. Firstly, I'll go over the acrylic elastomer. The issue with the acrylic elastomer was that the viscosity was way too low, which makes it unsuitable for manufacturing processes. So if we want to make this one time in the lab, it would be feasible with a small amount of the acrylic elastomer. But if our idea is successful eventually, we'll see what happens. If our idea is successful in the future and we want to mass produce these materials and we want to mass produce these stickers that stick to your forehead, using acrylic won't be very efficient for manufacturing. So maybe PPO PSI would be a better option because the viscosity is much higher, which will allow us to improve the manufacturing process. So this is what the final formulation was decided in the paper. So the elastomer itself was PPO PSI. The paper still used PEDOT PSS as the conductive polymer, and they also include the silver chloride microparticles to improve the agglomeration. I also want to talk about adhesion. So the very cute gecko. So what the elastomer does is that it can still stick to the skin, but through a method called dry adhesion. So dry adhesion is a way of adhering two dry objects together, and it was inspired by geckos So geckos' feet are very dry, but they can still climb up walls. And this is because they have microscopic fibrils, and these microscopic fibrils stick to a dry surface and produce a lot of van der Waals interactions. Van der Waals interactions are quite weak, but because of the large surface area with the microfibrils, it does allow stickiness. So yeah, I found that pretty cool. And it's also very interesting that we can produce a material that has this effect to your skin. So yeah, that was the organic component of the material. Now I'm going to talk about the inorganic components. Unfortunately, Shimon isn't here to talk about the electrical engineering side of things. So I'm not very well versed in this area, but I'll kind of try to explain this part as well. So this is the actual wiring of our electrode, made out of silver nanowires coated in gold. I'll kind of explain the process in a second. So actually, let me show you this is the image that was shown in the paper. You can see at the bottom it points out the silver nanowire coated in gold tracks, AGNWA tracks. So this is the actual wiring that will be part of our product, hopefully, or it was part of their product at least. So what they did is that they first took a polyurethane sheet and they sprayed it with silver nanowires. They then coated the silver nanowires in gold, and then they used lasers to cut out the shape of the circuitry. So the benefits of silver nanowires coated in gold is that they are invisible to the naked eye. So it actually improves the aesthetics of the sticker that you're sticking to your forehead. People may not want to have wires on their forehead that's visible to everyone else, so it's kind of beneficial that we have invisible wires within the sticker. Another benefit of silver nanowires is that they're stretchable. So once again, we want the product to be stretchable. We want it to conform to the skin, which is why silver nanowires is a viable option for us. So how usable is this material? What are the how do we think the average customer will treat this product? So this product did successfully pass skin irritation and allergy tests. They used rabbit skin to experiment on this, but they also used human subjects. I want to point out that these human subjects wore these stickers for 24 hours. So this shows us the strong adhesion of this material, which I think is pretty beneficial for people who want to use this product on long term. I also want to talk about how using the material might affect its usability. So remember, impedance is quite an important property of this material. They found that 24 hours did not drastically make the impedance worse. It did reduce the impedance, or it did increase the impedance a little bit, so increased impedance is worse. It did increase the impedance a little bit, but it was a very negligible amount. Another experiment that the paper did is that they took the material and they literally stretched it and then let go of it 1,000 times. And this also did not drastically impact the impedance. Something that really is a concern, I believe, is that if the user is sweating, doing strenuous exercise, I guess they live in a humid climate, they'll get sweaty and the sticker will fall off. It really impacts adhesion. So that is something else that we should consider regarding this material. So yeah, that's everything. Thank you so much for listening.
I think that's one of the drawbacks. As we get closer to, I think it's one of the triggers just in general, it's inevitable with skin electronics, is that the closer and closer we get to something which is skin-like, the skin exfoliates. So that means, just keep in mind, this is something that has to be disposable and reapplied, because just like our skin, it exfoliates, reduces skin, we reapply it again, cream on it. So it's kind of natural that as as you get towards these types of devices that are developing, it does kind of it not may last as long as for say as something like my watch, for example. But it does serve as the most discreet and seamless form factor. So it's trade-offs. There's trade-offs for sure.
Mm.
But yeah, thank you, Rishti.
Yeah. Thank you for listening.
Yeah. To add, if I mean, I think some good pointers. I think back to the agglomerates and back to the actual. Where's the ingredients? Do you have ingredients here?
Which one? The overall ingredients that they wanted in the end?
Yeah.
A question.
Yeah.
How, like, once it's on, how feasible or practical is it to take it off
It should be.
and then put it on again?
Yeah, I don't know. They didn't say that if it was reusable or not.
So
I would like it to be reusable. If it resembles silicone, so I don't know if you like you can get these silicone sticky things for your skin. You can reuse them. You put it on, it sticks to your skin. You take it off, you wash it, and it sticks on your skin again. A little bit worse than it did previously. So I don't know the physical properties of these materials exactly. So
a lot of the times with these PSS kind of substrates or just certain ingredients, PSS usually, for example, even in a newspaper, I know how that was removed. That was just over time, you can wash it away with a cloth and just wipe it away. In this one, it might be something similar. Honestly, I don't remember. Out of my top of my head, I don't remember it going too much into detail in terms of the removal process. But I imagine it will definitely be quite, again, discreet and quite just easy, seamless. Because
do you think it would be you'd peel it off rather than wash it off?
Yeah, it might be a peel because of different ingredients entirely, which is what I wanted to talk about actually, which is the ingredients. So this is actually surprisingly really more complex than what I covered last week, and just in general actually. We got in contact with Santiago Velasco. He works at InBrain and Neuroelectronics, and he's a research engineer there, and he also worked in Cambridge in fabrication, in a similar topic actually. His PhD was on what we're building. And he looked at this paper and he told us, yeah, this is a very complex recipe, and the paper hasn't actually really detailed the recipe itself and steps to, basically imagine a cauldron and we're mixing certain things in. The cookbook isn't very good, basically. The cookbook is not very detailed, but it is very complex. The way they use cross-linking to form the agglomerates, it's actually quite new to these PSS. So to overcome concoctions. I don't think we're going to see how much we can take from this. We only have 2 months to develop. We're leaning towards off-the-shelf, which Riley Green's lab does have off-the-shelf materials. But in the future, we are looking to really take inspiration from how they have done this, because this material does outperform the off-the-shelf ones in terms of altogether performance. So I think it's really exciting to see. Yeah.
How long are you planning for the stick to be on? Would it be like you keep it on overnight, or is it like 10 minutes, like you move before bed or before shower?
It depends. So we're doing customer interviews to see how exactly people would use our product. Also, we have to consider the neuroscience behind what our product can actually measure. So we know that it can measure emotions and it can measure focus. I don't know if it can measure sleep. So we don't know if people would actually use it overnight, because people have their watches to track their sleep already, but people don't have watches to track their emotions. So if it were me, if I were a user, I would use this maybe an hour a day just to check in on myself. People journal. There are some people out there who journal for a few minutes every night. I think this would be another, for me at least, it would be an hour a day. For others, maybe an entire work day. Maybe they track their focus when they're at work.
Yeah, I'm wanting to know, there's 2 ways of saying it, because there's what we should say, what the customers want, and what the science actually backs, and we since we're even we're still in drawing board in terms of what we're actually going to mix into our cauldron pot in terms of like the actual substance itself. We don't know how long it will last, and we're going to reach that stage very quickly, I hope, in terms of actual prototyping and rapid development. But that could range from 6 hours, like naturally use one, to 24 hours, like more like this one plus. So it's see how far we can do. So in an ideal world, as long as possible, actually. Like, come on. I mean, if we just go on, it would be disposable, but that's only limited. We're only limited by the science and our development skills. So
a follow-up question about the. So would it be like it's actually a follow-up to his question.
Mm-hmm.
How reusable is it? So like, if you only do it an hour a day, you put it off for an hour, for example, you take it off,
Mm-hmm.
that same sticker will be used next day, and so or will it come in a pack?
Preferably, I would love it to be reusable, better for the environment. However, they definitely like you definitely will need to replace them. If it's something that sticks to your forehead, it'll gather bacteria. You're gonna want to dispose of it anyways. But yeah, I think it is also a beneficial business model for people to keep buying more and more stickers, which is what we were suggested by some on the commercial side of things.
Yeah. So one thing to know. So actually, when I presented lab 2 weeks ago, and I mentioned to Ben just how like Nanshu published a paper about what we're building, which is almost exactly the same. And the way that worked is literally just like it costs £200 to buy and then has disposable stickers. So you use similar fabrication to our previous work, PSS and a bunch of other stuff. And it had like a base component and then $20, well, around maybe cheaper, $10 to $20 replacement disposable modules that we can reuse. So yes, it is modular per se, and we're aiming for something like that. Yes, it's also like a big business model, subscription services. Yeah, but second of all, the science deems it so. It's skin. So that's exactly, yeah.
Like a toothbrush.
Yeah, exactly.
You have to throw it away after a while.
Yeah. Well, I hope you guys throw it away.
Yeah.
That's if you do.
This include the actual circuit, the EG circuit. Would these be sort of disposable?
Yeah, I think we want the circuit itself to be kept, and the sticker itself to be replaced.
So it'd be kind of like get your sticker, you put the circuit on, and stick it to your head, take the circuit, throw the sticker away, and you stick it.
Yeah, we don't know how we do that, but
yeah, so
we'd like to do that.
I mean, it's possible. We know that we have the tools and materials to do that, and what we do, ideally, I have the electrical engineers on our team explaining this to their coursework right now. But essentially, they're going to design the chip that sits in the fabric on the material, and then that stays. And essentially, that is like that stays wherever you go. You can just remove it and put a new sheet on top of the chip layer, and then put it back on your forehead. That's going to be our hardest things to decide on. It's really about what we decide to do and then build from. That's going to be a big step that we're going to need to research on, like how we're going to integrate this reusable thing. For our MVP, I doubt we're going to have a disposable thing. So just to note, ideal case, yes, it's disposable. But at the end of our lab placement, no, it's going to be one component. Just to if you see that we're documenting our progress, you'll see us actually just working towards one whole unit first. And if it does continue, then we'll try and make it modular. But yeah.
Cool. You mentioned that I think you want to put it on the forehead.
Yes.
Have you experimented with different locations, like for example, like the side, like behind the ear, where there's no hair still?
We haven't experimented with that. We have our electrodes and we've only used it on the forehead.
Yeah.
But yeah, I would also like to do the like behind the ears.
Yeah, it's an interesting location, and I know a lot of BCI companies are experimenting getting EG from the ear.
Yeah.
It's also more sort of discreet. Like I don't know where they would wear this. Maybe it's at home, so it doesn't matter. But depending on where on the forehead it is, like walking on the street or something.
We were talking about using the behind of the ear as the ground and reference electrodes.
Yeah.
Where we're taking the data and removing noise and things.
Okay.
If we were to use it behind the ear, would we use the forehead as the ground reference?
I mean, we're still using the forehead regardless. The reference could be the different reference. There's different reference points we can use. The most common one is here, but like around this spot for the ear. And then if we're measuring the like around the ear, I don't know exactly where the inner ear or around the ear casements are, but that's separate from the reference lecture. The body's a big place, and I think I like to bring Ellen to the stage. She's working on inner ear EEGs. What's so special about inner ear EEGs? What can you pick up?
Mainly processes from the temporal and occipital lobes. So yeah, we're also I'm using the reference and bioelectric from NIU. So that's what it's commonly done. I have a question about the paper. Did they do any use of are they picking up EEG signals, or did they just develop the patch itself?
They picked up EEG signals. Yeah, so I didn't include that. They did successfully. It was comparable to wet electrode signals.
Yeah.
How did they do that? So is the patch itself wireless?
Yes, it was. Yes.
It's a good question.
Good
question. Good point.
That is a good question. I didn't understand that part of the paper, but they did call it wireless multiple times.
Okay, because it's really interesting.
Yeah.
Usually you have some sort of microprocessor to make it wireless. It's like a huge thing.
Yes.
So, okay.
Honestly, that's a fantastic question. That's the question I asked when I went.
Yeah.
I was like, so yeah, they can measure it, but where is it sending off? Like, come on. I mean, it's a big question because otherwise it's useless, right?
Mm-hmm.
It was almost a perfect paper because it's like, oh wow, this is basically analysis to steal it. Okay, well, kind of. And but yeah, they didn't really go into that too much. At the top of my memory, NFC. NFC, have you heard of that? It's somewhat just very low power and sending data to the phone. NFC is like every Android phone has it. Who's heard of it? Yeah, very low.
It's kind of like Apple Pay.
Yeah, very low radio RF. So I don't know how it works, but that I actually don't know how they did the data processing for that too.
I think most of it was the materials part.
Yeah.
I didn't understand the electrical engineering side.
So yeah, what this means for our project is like, so we have a solution for the electrode. So the acquisition itself, but we've got the analog front end and then the whole S system on chip. That's a completely different side of the story. So that's what our electrical engineers are working on right now. That's actually not as complicated as you might think in terms of the actual circuitry. It's more about miniaturizing it and then putting it also on the skin. That's the hard part, like encapsulating in a biocompatible friendly form factor in conjunction with this and putting it somewhere nice, like behind the ear, for example, which is discreet, because it is big, as you say. Yeah, you were saying that.
No, you kind of answered it, but because it implies that there's a second device.
Yes. Yeah.
So.
Yeah, exactly. So this, again, I'm trying to dream up, I'm trying to visualize how this form factor would look at the end of the day to the consumer, because I did mention that, the ANA project is similar to what Nanshalu did 2 weeks ago, which she published. But actually, it was an ugly, very ugly device. It was basically just like the forehead around. I wish I could.
Is the face testing thing with the big battery?
Yeah, big battery in the front. So if I just.
Basically, yeah, the main things, the main bottlenecks to stop it being a seamless process is the battery and the microcontroller. So it's quite, I don't know, quite hard to make.
Yeah, so. Am I spelling tattoo right? I don't know. There was a very recent publication, and yeah, there you go. No, this is it. This is pretty. Literally in May 29th. Same day. That's it. As you can see, right? That's not something anyone would wear. So the whole point of ANA was to kind of like say, oh, anyone can wear it. Unfortunately, I don't look like that. I'm not sure about you guys. And the issue is that does have the AFE. That's analog front end and center from the system and chip, I believe. And yeah, priced about $20 disposable sensors. So yeah, it is possible. The chips, reusable chips, would cost around $200, which with each disposable sensor priced about $20. So that is pretty exciting that they can put it in that form factor. Actually, I might cover this paper in the future just because it's cool. But yeah, basically it's we might put the bulkier part in a different location entirely, just behind the ear. Anyway, we're still kind of discerning whether or not, or how and why the customer would like that and where. maybe is the best, maybe in the chest or whatever. But it'll be like there's two components to this, and physically, you see. So yeah, we'll see how small we can get.
Can I ask, this is for the room, because I'm sort of supposed to be doing user interviews. I did my first LinkedIn post the other day, and I thought it would get thousands of likes, it got like 20. So I've just been trying to ask people how they use a product like this. Like Christy and Jamil introduced it, we kind of have assumptions on what people would do and how they use it, but how would you guys envision like the use cases of this? So basically a seamless EEG that sits in the forehead and hopefully sends clean data to an app.
I probably put it on at the start of each day just to track my emotions, which emotions,
So
other states of panic.
yeah, that's one thing to note as well. It's like the sleep thing. We talked about sleep briefly, and yes, watches do measure your sleep, and they're actually pretty. My words are harsh on it, but it just measures heart variability and skin temperature on your wrist, which is very far from what's actually recovering, which is your mind. Many studies have shown that collecting EEG data is really beneficial. It's a completely different medium to understanding your sleep quality, and it makes sense because the Apple Watch and Oura Ring, they're far away from. The further you go, there's this principle that the further you go away from the organs itself to these extremities, the kind of more useless the data is, and that makes kind of sense. You want to go straight to the source, right? So that's exactly what EEG does, and that's why it actually in papers has been so beneficial to get these quality results from, quality insight from, which is what we're really trying to make here.
The key thing I say is like a consumer is this isn't something that I would put on if something had happened. Like if I felt in a moment that I was panicking, I would be calm. It's something I would always have running if I could.
Yeah, to add to that, I think the big kind of plus of the product is the fact that it's so seamless and like you can almost forget it's there.
Yeah.
So in that case, then it would probably be something that you would be using during the day, as opposed to just put it on for an hour and while you're sitting at your desk. It would be like you go through your day or even sleep with it, because having that kind of seamless, it's really easy and not that intrusive.
Yeah.
So
you forget about it.
Exactly. So I think I would probably do it for longer term and longer time periods throughout the day, as opposed to just like an hour block.
Yeah, currently we're thinking of just having a day, week progress, chronological progress, just monitoring, and then also that short bursts, like 30-minute meditation sessions, minute. But like just say EEG could measure anything, like alpha, theta, delta waves, all those, and you process it in the right way. What do you think you or like consumer would most want to get insights about?
I don't remember. What am I thinking about subconsciously? That would be pretty crazy. I don't even know how you do that.
Yeah, I don't know how we do that either. It might not be for everyone. Like not everyone wants to track their emotions.
Yeah.
But the way I envisioned it, at least me personally and like various people I know and members of my family, definitely would use it as part of like journaling routine, but also like through therapy. I know someone with bipolar disorder, and they're when they started to get insights into what triggers them, what triggers their emotions, when they started going to therapy and doing meditations and like understanding where their feelings are coming from, and understanding how to control their emotions and how mindfulness can also help their emotions and regulate their emotions, they start to heal.
Yeah.
So I think it is definitely beneficial for people. Well, I see it as beneficial for people going through therapy and wanting to improve their emotional states. Yeah.
The key one I like is trigger, because anyone that is interested in knowing like your own habits, how to set your own habits, you know that you activate habits when you have triggers, whether that be good or bad.
Yeah.
And I think it would be really useful for
visualizing when you have a good or bad trigger. Because like say if you like smoking, there's always going to be something that sets you off, something that reminds you of it. And you might forget that is the case if you can't constantly remind them, oh yeah, when I look at this thing, a spike goes off and I want to smoke. You can see there's a spike and then they're like, okay, I'll avoid that, and then you don't see more spikes.
Yeah.
That's what we're currently thinking. It's like that. You guys will so far, we just keep using the example, just say go on a walk at 4:30 every day for half an hour. And like everyone kind of knows a walk is good for you, but if you see a real time like that, or like at the end of the day when you check progress, oh, like at 4:30, like, or I was just feeling just more content on average, that'd be good. And then there could be unknown things that unknowingly stress you out as well. You'd be like, that's good. Call my moms.
Yeah.
And then you just figure out, triggers basically.
You know, say that this is like there's a lot of like data privacy issues.
We're currently
Yeah.
is
it best?
Yeah, I think we need to follow up on like years.
Because even testing on ourselves, this AP project, we kind of know about to be honest, it's a pure data room.
Yeah, I think we'll have to test on ourselves, but as soon as we start extending towards like in terms of privacy, like as soon as we start thinking towards customers or patients or trial.
Even ourselves.
No, that's because in terms of safety issue, not a data issue. Yeah, it's a safety issue in terms of like using personal safety.
Can I just go back to the material side of things?
Yeah. Sure.
Does anyone like maybe you hopefully? Does anyone have any critiques of the materials used in the paper or any kind of thoughts, any ways to improve it? Yeah, you.
I have thought, but it's probably not as good as if anyone else has a thought. So, I remember you saying that about the dry adhesion technique. And then a downside of that was experimenting, and then it would come off. Maybe there's a composite material system you could embed, which includes both that dry adhesion and some sort of wet adhesion to have a longer term.
Yeah.
I don't know, I literally have no clue that.
Gosh, we've got a really deep dive into what we can mesh together. I think that's definitely future steps. But ideally, if we can get a best of both worlds, we'll definitely explore that route. We're definitely constrained by what we have off the shelf in Riley Green's lab, and Joseph can provide for us. But it'd be exciting to see what we'd say in the pitch, because at the end of the day, we're going to pitch this to a few judges, and as long as we can say this is what we're headed, we're really excited to go in this direction. They'll understand. In 2 months, we're not going to create the one product. So
like this is not just like a 1 month, 2 month thing. It's good for us long term. So maybe it's something that someone wants to do, like a PhD.
Exactly. Which is why we're so heavy on public documentation. So someone else can just carry on and just continue the project. Cool.
I think the more people trust it, the more they will not want to take it off.
I mean, I don't take this off. That was I'm sure that was way back in the day, but now it's back in the day. Things are changing. There's a saying, so there's this quote, that science progresses one death at a time.
Wow.
It's a bit peak, but it's kind of extreme. But there is some insight, I think, because what we consider normal isn't what's normal in the next 10 years.
Is the emotion, are you guys sort of like doing the whole, like, what is it, like 5 or 6 basic emotions, and then you're saying any one emotional state is a combination of those? Or are you saying you're scared?
I think Karen and I will be working on terms of how to classify the emotions. I think we're constrained by the data sets that we're training on. That usually is like arousal, focus, happy, sadness. I think it's like 5 emotional states that we're quantifying. And that's based off the machine learning models that are publicly available, and we're trying to train from the data sets that they trained off. But the basic forms. Starting from there.
I would recommend doing something along those lines, because when this other startup I told you about, cool, they try to decode emotion. You're never feeling just one at any time. It's always like a random combination of things.
I think that's where it would be helpful to have a multimodal, like measuring not just what EEG provides, but also just all sorts of biomarkers and health metrics to paint again that full picture, to capture all the mixture of emotions that do exist in every human state.
And do you know, could you tell me anything about how coding emotion or decoding emotion works? Because I've just started looking into that. I'm working on the project, and it's you basically take a Fourier transform of whatever EEG is that you have. You break up into alpha, theta, delta, theta waves, and then the relative levels of amplitudes sort of related to your cognitive state. Is there more to that?
Yeah, so basically when the startup Google I was doing it was they took the main waves, like you said, and then they were essentially just, there was a pipeline built out where they were just trying to sort of decipher any sort of latent variable, whether it was the amplitude or whether it was some other, I can't remember all of them, and then they would chuck it into these different models. And whichever one got the best sort of predictor, that one was sort of like the winner, and that's the one they used. But
How they predict? They just you label that data, or is you use it as the patient saying, "Oh, I feel this emotion"?
they got a bunch of videos off YouTube, and they were basically people were watching that stuff, and then they were wearing the thing, and they were labeling the thing. So there was labeled data. And it was, to be honest, it was kind of hard to collect because, like, obviously, fine, you can watch like happy videos, but then there's disgust videos, and then there's like, you know, sad, and like they have to be like, it has to be quite like potent, like the person has to really feel those emotions, and it's draining to like collect data because like we were just talking about Black Mirror episodes, like it's, you know, you can't just. And then all of a sudden I'm happy, and all of a sudden I'm disgusted. I'm like, I'm watching death. I'm watching like a marriage. Like it's just like, whoa.
Yeah, if they're doing one at a time.
Yeah.
I feel like if I'm watching some gore, and then it's a video of puppy, some residuals from watching me gore, but you won't be there.
Yeah. Or like I don't like jump scares, but when I was like trying to, you know, I'm like waiting and I'm like scared to watch this scary video, like it's all
Yeah, that's something.
You just Ben, you might be really interested in something called Hume AI EVI models. These are empathetic voice interfaces. They're one of the most accurate that I've come across, just capturing all the dynamicism of human emotion, all the multifaceted nature of it. It has its own proprietary model. And if you go into here, it's real-time customizable voice intelligence, but expression measurement, there you go. And it uses different factors, so the facial expressions, but the voice tonality from the ground up to just trying to discern what are you feeling. It's a combination of a few things. And it's really cool.
Okay, yeah, I'll take a look at it.
Because but the thing is, this doesn't take into account health metrics, so it's actually funny, but this is very just visual. It's really cool.
Yeah, the emotion thing is like super tricky, to be honest. Like, if you start incorporating like heart data, all of a sudden you're gonna get better metrics because it's like, is it coming from top down, or is it coming like it's a weird thing.
Oh, is that a thing? Like emotion spreads so that you can feel it in your heart?
No. Because you feel scared, you will have like a heart rate. So like,
It's always top down.
figuring it out.
We're learning.
You know,
Really put my toes up.
much easier.
What was this? What's this?
But then all of a sudden you have like emotional feelings, all these different things.
That's why when you tickle people's feet, they start laughing.
Because
Bottom up.
Yeah.
So yeah.
It's better when you have emotion.
Yeah.
That's great done. Yeah, Joe was saying the same thing. I think sometimes with EEG it's hard to interpret. Yeah. Like you could have two very good signals that are very similar, but you could be experiencing two different things, and you need data from your heart or you sweat or something like that. So.
Yeah. Like reproducibility was. I had to deal with this struggle of EEG just being so useless because you don't get the same reading twice. It's just not going to happen. It's so hard So again, we fill in the gaps by using different sorts of metrics, not just EEG. That's ideal. That's ideal.
The other thing I was thinking about is like when you were talking about artifacts, if you train a model to sort of separate out those artifacts, how well does that scale to other users? Like, are my artifacts, is that model going to generalize to that same age group that, just the person?
Yeah.
I added like emotional aspects, like if you blink versus the right.
Or
Stuff
the
like
jaw movement, like how easily is that generalizable?
Yeah, I mean, again,
I think it's like, I think that's why it's hard to commercialize. It's just the general public. But if you think about prosthetic limbs, why they take so long, why they're so rare, because and data collecting individual patient data and understand how they work. But yeah, it's interesting. It's interesting. I don't know whether you can generalize it for emotion. Just say it doesn't pick up any emotional aspects. When you just have clean raw brain waves, is that even generalizable as well?
I think I'm confident with the emotions. I'm confident with the emotions just because it's been done before. There can various different test subjects and patients. But that's been done for a long time. But I think when we start to do what we're doing, and it's more custom. And where it needs to be like reproducible. There are like lots of advancements. This wouldn't have been possible the last few years, but like calibration models, zero calibration, so machine learning models that and some that requires some calibration, some that does and some doesn't. And I don't know how it works actually, if I'm being frank, but there are avenues we can take ideally that to really tailor. Kieran mentioned prosthetics, and that's true. UCL researcher, he had head of his own lab. I forgot the name. He designs like EEG based prosthetics, and literally how they control their limbs and how they control the wheelchair. It's like they train it off the motor imagery cortex. So this on top of your head around here, and that's trained, that's calibrated for that person and constantly calibrated for that person. Like because the brain rewires itself. It actually gets stronger. It's like a muscle. Imagine having a sixth finger. It's really weird at first. You guys can't imagine having a sixth finger, like just because we don't have it, right? But let's say you suddenly grew one. It's kind of like learning how to use it, which is almost. But I go off on a tangent. Just about your question specifically, we don't know yet.
Yeah, it's just like a common theme. Like for example, I don't know if it was the wrist-based like EMG deciphering. So for example, like moving something, Metal is doing that, where they had something on the wrist, and then they were sort of like, okay, you want to move. It's like a cursor for their thing. Yeah. But you train it on X many subjects, but then as soon as like a random person, a random other person tries it, it's not as like. It's not as accurate. Yeah. And like the things with these things is like, with this cursor thing, it has to be on par with the current cursor, right? If you twitch the mouse 1 pixel on the screen, it's going to move 1 pixel. So people have an expectation for that very, very high fidelity. Yes, yeah. That's definitely something we need to consider on a commercial aspect. And I think, you've heard of Neurable, the company? Yeah. And they have these MW50 headphones that measure focus, and they have that's a consumer level product. Everyone can wear it, and they claim everyone can measure the focus accurately with this device. And they have a calibration system for a while to calibrate the person on their product. We could maybe, in theory, adopt such an approach, but I don't know how that would play out technically. It's just something to keep in mind. Yeah, you're right.
It'd be amazing, like if there's an EQ project that you let infinite time and infinite money, just take data from as many people as possible. Maybe if you take data from X amount of people, maybe there's some generalizable concept that really advanced AI can pick out. But I don't know. I've looked at a lot of consumer processes side, and I'm quite cynical about it all. But I'm trying to be optimistic. But I think it is quite individual. But I don't know. But you just got to look for commonalities. So they're like just if the shape of the wave is different, at least maybe for example, like a blink or a hand twitch, there's an amplitude you get, which is much greater than just the movement. And then you can remove it like that. Or I was with a patient in a study the other day. There is ways to tell whether you food and that just gets cut out instead. It's just too much, just like denoise.
Yeah.
But yeah, well, that's all stuff we're going to discover in 8 weeks. But
Yeah, I mean, Kieran's coming on next week to present his paper on the machine learning side. Hopefully that'll be fun.
I'll just see you guys there. 19th.
Yeah.
19th.
Yeah, this time next week.
So that'll be fun to see what we can do on that side. But I think it covers up everything.
Yeah. Sorry, did you have
Any questions?
you had something to say, but that was ages ago. Sorry, you must have forgotten.
No, okay, I can remember. It was the question about the consumer use.
Yeah.
I kind of like the idea of you mentioned journaling. And
Yeah.
I thought that could tie quite nicely into it.
Mhm.
If it's like if you, for example, you have your day structured on a journal kind of timetable, and then you use